throughout this year on learning analytics at Michigan. And I'll say a bit more in a minute about why it is we decided to try to organize a seminar like this and what it is we hope we're going to do. I'm going to talk about that a little, but mostly I'm going to talk about a particular project in learning analytics here at Michigan, something we've been doing around the Department of Physics that involves trying to understand what the records of 49,000 students can tell us about what happens in our classes and influence maybe how we might improve what happens in our classes in the future. So to introduce this seminar, I want to say a few words about learning analytics at Michigan and why at Michigan. So Michigan, I believe, is the leading public university in the world. And it's our job to educate enormous numbers of people as well as possible. And one of the things that I think we need to do it better than we do right now is to pay more attention to the very large quantities of data that are available or that can be created in order to understand what's going on in a room like this. When I arrived here in 1995, I would go in to teach a class like this with 500 people in it, and I really had almost no idea what was happening out there. And it was very difficult to get interaction in a one-on-one kind of way with students. And I don't mean one-on-one like I individually talked to them. It was difficult to even have a lot of information about all of those students. That's really changed, and it's changed because technology has really changed. So it's now possible for us to use technology to address these individual students much more directly than we have in the past. So why learning analytics at Michigan? Because I think we should be a leader in this kind of area. Educating people at scale is something we do here. This is Michigan. Now, there are people who would tell you that it's something else down the street in the football stadium. But really, this is what we do at Michigan, is educate a lot of people. And I think we should be pushing to do it as well as possible. So with this in mind, and with an understanding that there is a big community of people on campus doing learning analytics kinds of things, we decided to put together a symposium, a seminar on learning analytics here. And I did this because I wanted to know what everybody else is doing. And there aren't really the right forums for that. So we thought we'd try to bring together people who are interested in understanding anything about the academic mission, from admissions to individual classes to what happens with study abroad, whatever it might be, through the analysis of data. So what we did is we applied for one of these Rackham Distinguished Faculty Graduate Student Seminars, and we're lucky enough to get supported by that. We have, in addition to the seminar, put together an M community group that probably is where you heard about this, Learning Analytics at UMich Study.edu. And we've set up the first few of these seminars. We're going to do them bi-weekly. They'll be here from 12 to 1, basically. And the first few are listed right here. Some of them are from here on campus. A couple of them are from off campus. So we'll have John Campbell come from Purdue to talk about the Signals program at Purdue. This is a program that is designed to look at information about students in order to recognize students who are really at risk of failure. We also have Dave Pritchard coming from MIT. Dave Pritchard works in the physics department at MIT and has done some really creative work with online homework systems, and in particular in the analysis of data from online homework systems. They did a lovely study where they show that if you actually spend less time on your online homework than it takes to read the homework, you will end up 2-letter grades lower than you would have otherwise. Right, so they can see the impact of cheating in online homework systems because that information is all there. Anyway, if you have a topic you would like to talk about in learning analytics, I would love to hear it. We would love to have you talk. So I'm looking for suggestions from people. Please send them to me and we'll try to schedule people through. This is what we've got for the moment. All right, let me talk about this physics project. Every term in physics, about 1,900 students take introductory physics here at Michigan, and they do that in 4 different courses. There are 2 sequences of 2 classes. Everybody takes it for 1 year, so they'll take a first semester class and a second semester class. All 4 of those classes are running in any given semester. I've worked a lot on introductory physics courses, so have many of my colleagues in the department. It's a focal area for us because so many students are in it, and also because for many of these students, it's their only interaction with physics. So it's really important that these classes should be as good as they can be. And we've done a bunch of things, taking education research from the physics education community over the last dozen years or so. We introduced electronic response systems here on campus with very clunky early technology. We use online homework systems, a whole bunch of different things that we've done to try and make the classes more interactive, more engaging, and more relevant for the students. Naturally, we would like to know whether this has worked. And so we've done the things that we knew how to do then. We look at aggregate outcomes. We did things like give old exam questions to see whether students actually can do better on them than they did in the past. We look at the self-reports of students. We ask them, did you find this new thing that we did valuable? At least we would like them to think it's valuable, even if it actually isn't. We would hate to have them say, no, it clearly was not valuable to us. So self-reports, that's sort of useful. The experience of instructors is also somewhat useful. None of us really know in detail what's going on with all those students who are out there, but we do have some sense of what's going on. So we were paying attention to this, trying to understand. And then in 2008, we started a project called the Better Than Expected Project. And it was, I'll tell you where it came from. The people who were involved were Dave Gertis and Gus Everard and myself on the faculty. And 2 undergraduate students have played a big role in doing some of the analysis of this. Lori Lai, a physics student who is now a law student, and Kate Miller, a physics student who's still working with us on these projects. So what was this Better Than Expected project about? Well, it was inspired by some work that Scott Freeman and his colleagues did at the University of Washington. And he came here and gave a talk about this work in around 2007 or so. What they were trying to do is they were trying, first of all, to reduce the number of students who failed introductory bio. Because introductory bio is a gateway course for an awful lot of things. And if you fail that class, it's really hard to go on. So that's what got them started. They wanted, though, to understand when they made a change to their class, what it did to everyone, and not just the students who came in at risk. And to understand how this change affected everyone, you need to have some idea of what you expect everyone to do before they even start the class. If you know what you expect them to do, and you make a change and they do better than expected, then you can see that something's changed. So what they started to do is they started to see how well they could look at the details of an incoming student and predict their performance. All right? And what Scott showed at that seminar that I saw was this plot right here. They could predict the grade of a student with what seemed to me at the time surprising accuracy. And in order to do that, they really needed pretty much to know just one thing. What is your University of Washington GPA before you take this class? So essentially, they discovered that A students are A students and C students are C students, right? And that's a really interesting fact because there are actually very few students who are A students in one subject and C students in other subjects. What makes a student perform the way they do is a rich toolkit of stuff that they bring to the class. It's much more than just the details of whether they're the kind of person who gets mathematics or the kind of person who understands English literature. It's more than that. I mean, it's partly that, but it's more than that. So I saw this and I thought it was really interesting and realized it would be really fun to try and do it here. So we set out to replicate this kind of study here at the University of Michigan. We took M-Pathways data about students and used it. We pulled out data about the student at the beginning of the class and used it to predict student outcomes. All right? Our goal was to identify students who did better than expected, find students who did worse than expected, and figure out why that happened to them. Once we know who they are, maybe we could understand what it is that makes a student actually overperform beyond what you would expect, what makes a student underperform. This is the University of Michigan, so there's a lot of data. The M-Pathways system contains data back to 1996 of this kind, and we have a 14-year data set with 49,000 students in it. So a lot of information. They're in those 4 courses, those 2 sequences that I just told you about. Now, we came to this project with a particular perspective. And the perspective that we had as physicists was from doing cosmology and particle physics. All right? So I'm a cosmologist. And my research involves looking at hundreds of millions of galaxies. And every one of those galaxies has a whole lot of properties. It's a really rich object. It has a shape and a size and location on the sky and a brightness, and it's made of certain kinds of stars, all this kind of stuff. In particle physics, you have hundreds of billions of collisions, each of which is measured with thousands of numbers, right? So we started to think that looking at students is actually the same as this. We have thousands and thousands of students, and they're all really rich, complicated things, right? But in principle, it's not that different from what we do in our daily work. So our toolkits, the way we've done this, and to a large degree, the sensibilities we bring to it, come from the analyses we've done in our own work. All right, so what does this data look like? This is the kind of data, it's not every bit of it, but this is the kind of data that we have. There's a bunch of admissions information about the student. Where were they before they came to the University of Michigan? What was their performance like before they came here? So all the stuff that you might find in an admissions packet for a student, including standardized tests, but also information about what their background is like. Are they a first-generation student? What's the socioeconomic status of their family? Then there's a bunch of information that relates to their performance at Michigan before they started this term. Everything about that. Their cumulative GPA, how many credits do they have from here? Are they a transfer student? What's their age? Are they an athlete? All this stuff lives in the mPathways data set. We add all that stuff that tells about them before they arrive in class to information about what they do in the class. These large physics classes have a very organized structure, and so we actually have the internal course grades for many of the students in these classes. So we can see what they did on different assignments, how much of their homework they worked on, what scores they got on those things, how their exam grades progressed through the term. Did they get better? Did they get worse? All of those kinds of things. And then finally we see the grade they receive in the course, and we can find out about other courses they took at the same time. We can learn about the number of credits they were taking this term, everything like that. This is really just part of what's available in that kind of mPathways data set. It opens the door to asking and hopefully answering an awful lot of questions about what's going on campus, and I think it's been pretty seriously underused. Okay, so what are the essential findings from this Better Than Expected project? First of all, we see the same thing they see at the University of Washington. You can predict student grades based on who they are when they arrive to about a half a letter grade dispersion. Okay, so we can tell what grade you're going to get. And the most powerful predictor is the University of Michigan GPA. There's additional information in some other things, although it's pretty correlated with GPA, in SAT, ACT math scores, things like that. That's one message, that you can predict people's grades. The second message is that there really is dispersion in this. That even though you can predict grades, different students have different outcomes because they do different things, and we want to understand what those things are and where they come from. We have also been able to show that there are significant performance disparities in this data set that are related to parameters we don't think should have anything to do with the student's performance in the class. And they are related to gender, your first-generation status, and your socioeconomic status. And I'll show you some of the results about those. But first, just some really basic things about how well you can predict the grade. So here's a figure. Let's just look at the upper left corner to show one of these figures. This figure shows on the x-axis the student's incoming University of Michigan GPA. All right? On the y-axis, it shows the average grade for students with that GPA. And that grade is on a 0 to 4 scale, so a 4 is an A.
If you don't mind if I interrupt you, but
please.
What is the GPA if the student is a freshman?
So all of these students have been through at least one term, which is true for almost all of our students in introductory physics. Engineering students typically take it in the second term. So there is an interesting thing to ask about, what about very first term students? Yeah. They're not here because we don't have that information. Okay? That GPA becomes a tighter and tighter correlate as they go along, not surprisingly, because the first term could be a little different and everything else. A lot of interesting questions you could ask there, right? So what we've done is to take each bin in University of Michigan GPA, measure the mean grade for that bin, and that's what's shown as the points that have error bars there. And those are the errors on the mean, and if you care, they're determined by bootstrap resampling, the kind of stuff we usually do. So those are the means and the errors on the mean. The dotted lines that you see on the outside are the 1 sigma dispersion around that mean. All right? I don't just put up the data points because it's just a solid blob. There's 49,000 students, right? So this is a digestion of that. The line that you see going across the solid line, that's a 1-to-1 line. So if students got the same grade in physics that they have for their typical GPA, would they be on that line? They're not. They're below it. Students do worse in physics than they do in most of their other classes. I don't think that's going to be a big shock for anyone. Okay, the correlation coefficients are also shown up there. And then these other plots show the correlations with some other parameters, like the SAT math score. There's still a reasonably significant correlation with that. The ACT math score, much weaker. Age, nothing at all, really. Okay, just to show that you can do this kind of study, you can look at all these different parameters. Okay. So let's look at some of those performance disparities that I mentioned. So let's look at gender first. This is the one that I'm particularly concerned about, the one that makes me craziest. Okay? So what we see here is essentially the same figure, GPA on this axis, average grade on that axis. The data points are the means and the errors on the mean. There are a top set of points that are diamonds, a bottom set of points that are triangles. The top set of points are the male students in these classes. The bottom set of points are the female students in these classes. There are two sets of dispersion lines. The dotted ones go with the male students. The dashed ones go with the female students. There's a very strongly detected gender disparity in these classes. I have to say at the outset that this is seen completely nationwide in introductory physics courses. It's not something that's special here. That doesn't mean we don't hate it. But it's not something that we only see here at the University of Michigan. Okay? So there's also another thing to remember from this is that there's huge overlap in these distributions, right? So it's not like everyone is landing on the mean here. Any individual student may land anywhere in this.
So has anyone looked across the nationwide data about this at instructor variation?
So we've done some of that here, and I'll show you a little bit of semester by semester data here. There have been some studies done of that, and they don't completely agree. There have been claims made that the gender of the instructor can have a strong impact. But those claims have not been supported in other studies. So there's at least other factors. It's not a really simple thing to make a difference. Okay, you might think maybe this has to do with SAT scores. Now, SAT scores also have gender differentials. But in our data, what we see is that even students who are getting 780s on the SAT show a gender difference that's about this large. So there's something else going on here. And we have a lot of ideas about it. But now we know what it is, at least. That's really what this has enabled us to do. And I should say that a bunch of this, the work on the gender disparity was done by Kate for her honors senior thesis. So let me show you a little bit of semester by semester stuff to kind of get at that. This is not a great illustration of it, but I just want to show that in a typical single semester, in a single course, we can show you that the incoming as students come in, female students enter with stronger U of M GPAs. And if you just, the female students are diamonds here, the male students are pluses. If you just look at the high end there, you can see the female students are preferentially populating that high end. The two lines that are drawn on this figure, the dotted line is a male median, the dashed line is the female median. So you see they come in doing better at the University of Michigan. Then if we look at their grades in these classes, this is Physics 140, the engineering class, their grades, their outgoing grades are lower. So even though they come in looking like they're going to do better, they go out doing worse. And you can see that term by term. There's enough statistics here at Michigan to do experiments in single terms and to really be able to detect the effects. That's an opportunity in a way for us. If we have an intervention that we think will work, you don't have to wait 10 years to find out whether it does. Now, let me try and explain this one. This is more of a physics kind of a thing. Each of these plots is for one of those four classes. Each point on the plot represents a single term for that class. And each point on the plot shows either the pluses show the incoming GPA difference of the students. The diamonds show the outgoing grade differences of the students. So the x-axis is the difference of either GPA or grade. And the y-axis is actually the Kolmogorov-Smirnov probability that the distribution of grades or GPAs for male and female students are different. Okay? So if the distributions are different in a statistically significant way, you'll see a very low probability. And let me just call out these 2 points down here in the engineering sequence. So what we see in the engineering sequence is that the incoming GPA distributions are not that different on average. They're pretty similar. In fact, the probability of them being the same is reasonably high. But the outgoing grade distributions are very different, term by term. Each one is an individual term. So term by term, the outgoing grade differences are large and statistically significant in both of these courses. That disparity, if you look up at the 125, 126 sequence, you'll see that those disparities are not nearly as large. So I don't think I mentioned it, but what's the difference between these sequences? The sequence you see on the top, in the top two figures, is a life science physics sequence. That sequence is about 56% female. What you see on the bottom is the engineering sequence. That sequence is 23% female. So the gender representation in those classes is very different. Those classes also have a somewhat different emphasis, right? One is training life scientists, one is training physical scientists and engineers. So they're different in a couple of ways, but one striking way is the very different gender composition of the classes. Okay, let me show you another couple of things like this. First generation college students. Now, it turns out that if you look at the predicted grades for first generation college students based on their U of M GPA, those predictions work great. But if you look at it based on criteria of their high school performance, they're underperforming. So what happens here is a first generation student comes in, did really well in high school, got a 35 on their ACT, whatever it is. They arrive at Michigan, and their grades are already lower than they would have been before they get to physics. Right? You know, they're kind of underperforming even before they get to the physics class. So once you see that, you predict the physics grade in a way that is in agreement with the rest of them. But if you look back at the high school information, you can see these kind of differences. Similar things for low socioeconomic status students. Okay? So we can measure these things in the data. We know what they've looked like in the past. And what we want to do is to start to think about what we might do about them in the future. So, what's our job in introductory physics? Now that you've seen some data about it, our goal is to get this large, diverse group of students to learn physics. And it's hard. It's hard because the subject is hard, first of all, but also because the students are so different from one another. It's a really diverse group. They differ in their preparation, but they also differ in their motivation and their level of commitment. The biggest challenge for us is that there's just so damn many of them. If there were only 40, we would just get to know them and figure out what to do with each one. But there aren't, there's 700. So how can we deal with that? I believe they all really want to succeed, and so I started thinking about how learning physics might relate to other things that people learn that are really hard. You know, things like playing a musical instrument or quitting smoking. And when you think about other really hard things that people do, successful approaches to those always are aware of who they are and what motivates them. And if you don't do that kind of stuff, then it's going to be hard to get them to do the very best job that they can. So, what do we do to help them learn physics? We've set up these big, rich classes, and they have a whole bunch of tools which are designed to give every student what they need in order to learn. So they have all these pieces that you see on the side. Lectures, discussions, study groups, office hours, you know, practice exams, all these different things we give them. But we give them the same advice. Everybody gets the same advice. There's no kind of specialized interaction with them to tell them what we think they ought to do or anything like that. And each of these tools can be used in many ways. They can be used well, poorly. We came to have a sense as individual instructors that if you could give individual instruction to someone, you might make a big difference. If you can sit down with a student and say, what you need to do is not spend twice as many hours. You need to study in a different way from the way you've been studying. And you could only know what to tell them if you talked to them about it, if you knew what they were doing, right? So we had a sense that you could do something about this, but we couldn't do it because there's too many of them. So it turns out we can do better than this now. We can tailor our interactions with students and give them each specialized advice and feedback and support. This advice will be based on their background, along with information about exactly where they stand in the course and how they're doing. The technology for this actually exists. It will let us do all the kinds of things we're talking about here. And one of the things that I really love about this as an educational intervention is that it has something for everyone. This is not just an intervention that is aimed at catching students who are about to fail and making sure they get a C. It's also about a student who's going to get an A+ and making sure they become a physicist. Right? It's about everybody, because everybody has something that we want to tell them. Okay? So how are we going to do this? We're going to do it by taking advantage of the field of public health. So physics education and public health are both about achieving really important, really difficult goals. All right? One of them might be learning physics. Another one might be quitting smoking. Both really hard, both need a lot of help, not something that just happens. So we started to look at the field of public health as a way of thinking about how we could help with this. We did this because there is a record of tailored public health communication research that goes back into the 1980s. It actually goes back before computers were really all that powerful, but has developed a lot. A lot of this work has been done here at the University of Michigan by the Center for Health Communication Research. So let me say a few words about that. The Center for Health Communication Research is just over there, and 2 blocks from here. It is a National Cancer Institute Center of Excellence, a really big operation. It's a big operation because it has been found in public health that tailored communication of this kind is really effective. Instead of just giving everyone a brochure about breast cancer, you give people a tailored communication that knows about who they are and how old they are and what they care about and whether they have a family history and all of that stuff, right? Very similar kind of problem that they have. The amazing thing about this is that these guys have built something called the Michigan Tailoring System. It's done, all right? So what is the Michigan Tailoring System? It is an open source package, a complete product for writers who want to develop tailored content designed specifically for an individual based on data. So this is like incredibly obvious that we want to use this, all right? It's also, I should say, you see the big 3 there? It's actually in version 3. It's really pretty mature. It's used for a very large number of public health interventions, all right? It also has been highly commercialized. Here in Ann Arbor, there's a company called Health Media Inc. They sell products to people like Kaiser Permanente so that tens of millions of people in California can use these tools to control their diabetes or to lose weight or eat more healthily, right? The size of this in the public health community means there's a really extensive research base on the design of tailored interventions. And I'm going to show you just a tiny little bit of stuff. So to give an example, a tailored message might be very lightly tailored. This is the Ed McMahon tailoring that you remember from the 1970s when you would get a message in the mail that said, you may have already won $10 million. And it said, Dear Dr. McKay or whatever on the front. This kind of tailoring doesn't work so great because everybody knows it's fake, right? So this is low-depth tailoring. But there's no reason using this kind of computed intervention that you can't do very high-depth tailoring. That you can construct messages that use all of these pieces of information to design what you want to say, to change the information that you want to send, right? So they've done a bunch of research in the public health world about the impact of depth of tailoring. Design a study where you have a smoking quitting thing, you give everybody Nicoderm patches, you give them low tailored messages, or you give them high tailored messages, and you see what the outcomes are. All right? A lot of people are trying to quit smoking, so they have great statistics. Here's just an example. As you increase the number of highly tailored components, it works better. This is not, I think, a miracle, but they can show how much it works better. All right? And there's a very big literature of this. The CHCR web page has a whole pile of stuff that you can look through if you want to know more about it. They have begun to investigate much more subtle details about the tailoring. Which parts of the tailoring really matter for different interventions? And because they're doing these big studies, they can actually begin to pick that apart. They've worked with the statistics program here to design fractional factorial designs for studies like that, so that they can change many parameters at once in the study and still extract information about which parameters were most important. So a lot of interesting stuff that's purely Michigan. You know, the Michigan group here working with the stats department here, it's really great, and I didn't know about it before recently. They've learned that testimonials are very powerful. To have someone tell you what happened to them, how they quit smoking, how they learned introductory physics, really works. But it works best if it's fully tailored. So the person who's telling you is someone with whom you identify. You're a pre-med student, you're scared to death of this class. If a pre-med student who was scared to death of this class tells you how they succeeded, it works a lot better than if Dr. McKay says, here's what you have to do. Right? It's just different. So in public health, I was surprised to find that they completely make up these testimonials. Right? They have this suite of pictures of people that they can stick in the testimonial so that the picture will match you really well, even though it's a completely made-up person. I don't know what I think about that yet, but that's where it is. This is from their website. They actually got an NIH grant to take all these pictures and make them available to people so that everybody could make up their testimonials. So I guess it's the standard of the field. You see, I've clicked off amused and confident and content, and you get a picture for all of these. You choose the age, you choose the ethnicity. It pops out pictures, right? Anyway, the public health community has been thinking about how to get people to change their behavior a lot more than I ever thought about how to get people to change their behavior. I mostly thought that doing physics was about understanding Newton's third law. And of course it is. But to get there, if students are going to do better than they would otherwise, they have to change their behavior. Otherwise, they're just going to do whatever they were going to do, right? We have to get them to study better, study in smarter ways, maybe study more. It depends on who they are and what they're doing. So the public health community's thought a lot about what will affect the outcomes of people. Things like motivation in the sense of self-efficacy. Things like their ability to understand how good they are at this. People are really bad at judging how good they are at something. And you see that with students when they say, I'm ready for the test, and then they aren't. Right. So there's a lot of literature here that I'm finding very interesting in thinking about how to understand where students are in this and then what to do about it. So this is the same thing about behavior change. They've been thinking about it a lot. They're way ahead of most professors here at the university in understanding behavior change. And there's a lot of good tested stuff out there. And so we're trying to put some of this material to use in using this system. So how did we get involved in this? How did physics and public health get together? I like to tell this story because I think it's an Ann Arbor, University of Michigan story, right? So normally I don't go to public health talks, right? But I do things in Ann Arbor, even things off campus. And once I was in a musical. Okay? So that's actually me on the left there. All right? I'm the guy with the teaching problem. The guy who invented the tailoring stuff is this guy in the middle. Okay? So I knew him from the neighborhood, Vic Strecker. He was just a guy I knew. And then in 2010, he won an award. And because he was my friend, I went to see his talk. I had no idea what he was going to talk about, right? And what he talked about was this stuff. And I sat there listening to the talk, and I wanted to jump out of my chair because this guy was ready to solve my problem. He had the same problem we do. How do you give expert advice to a large, diverse group of people? The difference is he solved it already. Okay? So we started talking to Vic's group very quickly about what we could do. And he started looking for sources of support that might enable us to try this over an LS&A for education kind of projects. And we found this thing called the Next Generation Learning Challenge, which came out last fall. Money from the Hewlett Foundation and the Gates Foundation run through EDUCAUSE. They put out a call for proposals. There were 650 proposals, 29 were funded, and we were lucky enough to be one of them. So we're now building something that we're calling eCoach, but we put a little squared on it. There's two reasons for this. One is that we want it to mean both electronic and expert coach. And the other is that eCoach has already got a trademark. Okay? But E² coach doesn't. So I don't actually know if that's going to be good enough for intellectual property rights, but whatever. There are three groups of players in this: the Department of Physics, the Center for Health Communication Research, its leadership and its staff, and then we're trying to really leverage Michigan, right? Because there's experts on everything at Michigan. And so if we want to use values affirmation approaches to trying to change people's performance in physics, something that has been shown to reduce the gender gap, we can talk to people who know about that here. And we're trying to do that. I'm sure we'll fall far short of fully doing it, but we're trying to do that. Our goals are to improve the performance of everyone. Everyone should move up. Why not? Right? We want to reduce these disparities. And we would like to have an impact on students' impression of these things and their persistence in STEM degrees as well. So what's the project looking like? This is the chalkboard from yesterday. They can testify, it really is. This is what we wrote yesterday morning. The people who are doing this, there's a team of people, like I said, in physics and in CHCR. It's me and Kate Miller, Jared Tritz, a new employee here, Gus Everard and Dave Gertis in physics. Over in CHCR, it's Vic Strecker, who's the director. Ed Saunders is the assistant director. Holly Derry is the head of behavioral sciences there, an expert on tailoring. Mike Nowak is the technical lead there at CHCR. So what are we doing? We're trying to design this project. It has in the middle the Michigan tailoring system. That's what makes it possible for us to do this. If that didn't exist, we wouldn't be able to do this. We need to feed a number of things into it. Some results will come out the other end. We'll close the loop and do some research. I'm going to show you some of those pieces. I'm going to tell you where we are right now. So what are we going to tailor on? Where's the data going to come from? At first, I thought we would take the data from mPathways. Why not? It's there. It seemed like it was there. But then two things came up. First of all, it's not all there. A lot of things we want to know are not there. And the other thing is, we were really worried that students would find it extremely creepy that we knew all about them. Now, so we tried to walk away from this kind of precipice of creepiness by having the students just tell us everything we need to know, instead of taking it from this. I think that's going to work well. An interesting thing occurred, though. As I started talking to more students about the creepiness, most of them aren't very freaked out about it. Everything in their lives is public now. It's not true for us, but it's true for them. So they were less worried about it than I was. But I still think it'll be fine to just get the input from the students. Background, their expectations for how much work they think it's going to take. We want to be able to show them. You think it's going to take 2 hours a week? Here's what everyone else in the class thinks. You know, you're down here. So if that's what you think, okay, but you need to know what everybody else is planning to do, right? Stuff like that. In addition to the stuff they tell us, we will get information from the course gradebook. The details of exactly what's happening in the class. Pre-tests we give, homework scores, their electronic response in class, all of their exams. We may even include item level response in that. I mean, it's all possible to do. So what are we going to say? In order to know what advice to give, we have to gather the expertise that's out there. And so what we're doing right now, it's kind of up here on the top, instructor and student surveys. We've completed a set of structured interviews of all the expert physics teachers we have on campus. So we went out and asked them. We said, all right, if a student came in and this was their situation, what would you say? Right? And we recorded all that so that we can use it in the tailoring. Physics professors, it turns out, might not be the best source of this advice, because we mostly say what worked for us, right? You just keep studying, you spend more time, you know. At any rate, so we're also surveying Science Learning Center study group leaders. These are students who've succeeded in the class and are now teaching the class to other people. They're supporting students right now, so they're giving this kind of advice right now. So we're surveying them to find out what they would say. These will be our testimonials. Real Michigan students succeeded in that class. We'll tell you what they did, okay? CRLT is doing a very challenging job for us of taking students who took these classes last term, for example, and did better than expected, or did worse than expected, and interviewing them. What did you do in class? What were your strategies? Right? And that's a very powerful tool for us. It's one of the things that I think will be really important. So we have some initial results from that from last year. We're doing more of it. We're doing more of it now. And finally, we're trying to take advantage of University of Michigan's expertise in many areas. So that's how we're going to gather the expertise. That's what goes into designing the logic for the messages. What will we say? What are we going to tell them? Well, we're going to give them a series of communications that will come to them on a custom web page. So they'll have their own web page. Every time they go to it, it has their advice, their information, all of that kind of stuff. It will contain the tailored testimonials for them, the feedback on their performance. And it gets updated at every important point in the class. Let me give you a little picture of what a couple of these things look like. These are just some of the things we're going to advise on. We're going to try and give them normative information about how they should expect to work in this class. We'll give them testimonials from students at the beginning. And then as they go through the class, we will respond to their performance, especially after exams. The most important thing in these classes is what happens on the first exam and how you respond to it. So once you take the first exam, you're on a track. And if you don't change your behavior at that point, we know what your outcome is going to be. So that's a really key point, and we're really going to push to get people to do better things after their first exam, no matter how they do. Okay, so what does it all look like? This is the workbench for the Michigan tailoring system. I said it's a very sophisticated set of software. It lets you code these things. So in here you can see, hello name, welcome to eCoach. And over here you see a live preview of what that thing might look like. So this is how we write this stuff. We couldn't do it if they hadn't built a really rich, complex project or tool already. It even has, a versioning system built in. It uses SVN and everything else. This is I work with lots of software from lots of my colleagues in science. It's never this good. Right? It's usually written by a graduate student for that graduate student. Somebody else lets you use it. It doesn't really work. This is different. This is like a product. Testimonials. There will be custom testimonials like this with tailored bits all throughout them, right? So these are just some examples of things that we're doing now. For a student like this who has properties like this, they'll get a message that includes all this kind of tailored information. These are things that are coming out of the system now. So we have things working like this already. Just to give a sense of what it's like. As we respond to how they do, here's an example of something we're thinking about. I'd love to hear what people think about this. This graphic, it's kind of not very beautiful yet, but this is the idea of the kind of graphic we're thinking about. On the left is something that shows how the class breaks down. How much is each exam worth, the final exam? That's the structure of the class. On the right is the actual grading scale. Right? So students aiming for this thing on the right. After the first exam, we'll have information about how they did up through exam 1. Right? Those are shown as solid boxes here. If we take their exam 1 score and use it to predict exam 2 and exam 3 in the final, then we get the little dotted boxes. So if we did the most naive prediction, that's how they should expect to do at the end of the class. Right? What's shown on the side there, something we might or might not tell them. Here's what students like them in the past have done. We know that, right? So I can take a student with the same incoming GPA and say, how did they do at this point in the past? I don't know whether we should tell them that. I'm not sure. But we know what it is, so it's on there. And then as they go through the course, the second, third exam, the final exam will get filled in, right? So they'll have something that looks like this. At the end of the first exam, we were predicting they would be there, right? And I should say this is real students from real data. I didn't make this up. This is just from this historical data set. And we can do this for 40,000 students. So we can see how accurate our predictions are, all that kind of stuff. It's kind of fun. So this is a student, that prediction actually turned out to be reasonably accurate. You can see, though, that this student didn't do as well as a typical student like them at the end. The student came in with a 4.0 and ended up with a B+. Okay? So some thinking of what we're putting into this system. Where is it happening? Well, we promised the Gates Foundation we would launch this in January. So we're gonna, right? Again, it couldn't happen if it wasn't for MTS, and actually a heavy involvement from the health communications research people, right? They're really holding our hands. I think because they get it too. They think this is really good. One of the people on the list is Ed Saunders. Some of you probably know Ed from his time back in LS&A when he was a head of instructional technology back over here. Okay, so we're going to do what we can in January, and we'll be able to test its outcome. We'll be able to close the loop and see how they perform and study it against what we knew in the past. So that's what we're aiming for. Then we'll have a spring and a summer to try and enrich it, to add some new pieces to it. Maybe let them ask for help at different times. Provide that. Maybe give them new kinds of tools they might be able to use. Set up a better testing system in which we tailor in one way for some people, in another way for other people, and then look at the different response. So that's what we're aiming for the fall semester, is to enrich it, make it work better. Right, research, yes. So I think this thing is the Michigan difference. This is what we really do. And I'm imagining a future in which computer technology will be tailored in this way for people. It'll give every student assignments that are adapted to where they are right now, help them get to where they need to be, help them find more effective ways to work through individualized coaching. I think that a system like this, I'm sure, that a system like this can do it much better than me, than any individual person, because there's just too many people out there. So it's got to be better than what we're doing right now. A system like this never forgets who somebody is, never fails to pay attention to the details, and it has time for everybody, right? So I want to see Michigan play a really leading role in this kind of thing. It was invented here, let's use it. So, and I'll stop there and take any questions you might have. Barry.
First, bravo. You're doing when you're drawing across multiple disciplines, which is always the way to get the best innovation.
We hope so.
So you're a real model of how to think about this. My question is a specific one about where you might hope to go. Mm-hmm. So it looks like all of the feedback right now is about behavior, how to change your study behavior.
Right.
Is there any thinking about using the tailoring system data to actually change what kinds of physics problems you give different kinds of learners?
Yeah, I mean, it's clear. We want to have adaptive tutorial systems like that. The only reason we didn't include it in the beginning of this is that there's an extra layer of technology that's involved. We did, if you notice in the list that I just had here, that customized coursework, right? So we're thinking about it. I just don't know how far we're going to get in a year. We use a very sophisticated system called Mastering Physics that came out of MIT. It was originally called My Cyber Tutor. Pearson bought it, turned it into Mastering Physics. It's very powerful, and it's easy to imagine hooking into it, right? Classifying problems so that you know if you can do this one, you should try that one, or if this one takes you too long, you should do another one. You know, the toolkit's almost there, but it's not here at Michigan. So we kind of held off on it, but it's clear that it's something we're going to want to do.
Will you have any way of like tracking student usage of this coaching system? So assume
right.
they're all going to use the same amount? Or,
Right. So we'll know when and how often they visit these web pages. That much we'll know. Whether they really change their behavior and how. There will be information you could use to dig some of that out, you know, like what they do in the homework system is actually all recorded, what times they do it. So for example, in principle, we can say, we noticed that you never open your homework until 2 hours before it's due. Right, because it's there. And we can go back and see if they actually change that behavior. We are trying to work with the CTools people to get CTools usage information. You didn't download the practice test. I would love to be able to say that to them, you know, if they really didn't. So that kind of stuff. We'll have some usage information.
And then actually another question, just quickly. So like, you know, the lecture classes are huge, but the lab context is a lot smaller. So is there any way that like eCoach could sort of interface with the lab?
Yeah, that's a great idea. You know, it is a place where we get on a small scale with people. They have actually GSIs in front of them who ought to be good mentors. I don't know if they always are, but they ought to be. You know, a system like this could take the same information and send a message to the GSI that says, these are people you should talk to about whatever. You know, I mean, it could do that. It's not something we're racing toward. Other questions? Yeah.
Like a question about the Pathways database. Does that have information that allows you to step through individual assignments, or is that the business department supplementing?
No. Pathways keeps what's on the transcript for students and what you need to run university, right? So they have grades. The internal course data is something that we have because we built a system in physics called SAMS back in 1998 or something like that. And then it became, for a while, supported by LSNA. It was a gradebook system, but a pretty rich gradebook system. So what we'll be using now is the Gradebook 2 system from CTools. So we'll be pulling that down, essentially, and looking at it. We can also pull the online homework systems information and bring that into the data set. So we don't keep internal course stuff university-wide. Would be cool if we did, but we don't.
Just wondering, is there any sort of pre- and post-testing in the class? So at the beginning of the class, give, for lack of a better explanation, that the final is comprehensive, but it's like we're trying to do the final at the beginning of the class.
Yes.
And say, how's this person going to my class with
Right.
these concepts and abilities?
Sure.
And then a post?
Yep. So are there pre and post tests used in these classes? So pre and post testing is something that's pretty widespread in the physics education community. They invented something, I don't know, it's almost 20 years ago now, called the Force Concept Inventory, which is a conceptual test you would give at the beginning and give at the end. It's a very standard thing. There's also ones for the second semester class about electricity and magnetism. We do administer both of those tests, the FCI at the beginning and the end of the class, and this thing called the BEMA, Basic Electricity and Magnetism Assessment, at the beginning and the end. They're great tools. They tell you something. They tell you how well students could answer those questions at the beginning and how well they can at the end. Those things are part of what the class is about, not everything the class is about. So it's complicated to, you know, I wouldn't use them as the only thing we're using, but we do administer them already to all of our students.
Does that come back into your analysis?
Yep. In particular, I think the pre-testing might be quite useful to know about. So, yeah.
So I have a question about the starting question. I mean, obviously, I think it's pretty clear that addressing, specific kind of behaviours is more likely to impact people who are lower achieving. It's more likely to make a difference on have some bad behaviors and
Right.
improving people who already have good behaviors. But equally, I mean, you can imagine that improving everyone is going to reduce disparity but not eliminate. And so I wonder,
Sure.
when you were talking about the design and who you were targeting, because obviously this sort of targets everyone to some extent, whether that's something you discussed and whether you have like a success metric, for example, for reducing disparity, that kind of thing.
Right. So we did talk about things we're going to measure at the end and see whether they're better, right? And one of the number one ones was these disparities. I would like to do whatever we can to reduce them, to make them go away. There are many people who are doing research on this kind of thing, trying to reduce these disparities. The one that was much in the news a couple of years ago had to do with applying a values affirmation exercise in the class. Now this is something that seems to have nothing to do with physics at all. You get people literally to write about what things they really care about. And in doing that, you can provide a certain amount of protection against threats to the self that might exist, right? At least this is the way the behavior change world seems to think about it. So we're trying to figure out how to incorporate these things, how to find out what students really care about, how to remind them of that through the term in the hope that it will affect these disparities.
Can I just ask one follow-up question?
Sure.
Because obviously one thing you could do to reduce disparity is focus resources on one particular subpopulation, but that's not something you're going to do, right?
No. I mean, we're not trying to, we really want to improve everybody, and there's a message for everybody. I think what's happening here now is that some people are underperforming compared to what they ought to be doing. And if we could get them back where they ought to be, then we'd be fine. Meg?
You might have said it, but is the course graded on a curve? Because won't you just then...
Sure, that would be a big issue. Right. So this is a tricky issue. Our courses are not graded on curve. We use a fixed scale that is announced at the beginning of the class. We do allow for one possibility. If the average or the median score in the class ends up below a B-, we will lower the scale so that at least half the class gets a B- or above. Right? But they're large classes, and we've taught them many times, and their material is very stable. So we usually hit it almost exactly where we expect to be. Now, if we make a change here and people start to do better, there's another factor in here, the feedback loop from my colleagues. And we'll have to think what we're going to do about that. One of the ways we wanted to, be careful about testing for real change was to reuse questions that have been used in the past as a little bit of a baseline. So we're going to do some of that. So it's a real issue. If everybody gets better, is my department going to be willing to give higher grades to everyone? I'm pretty sure they'll be hesitant. I'm going to have to lean on their conscience to really get them to do it and really prove that they're doing better, right?
And then would my kids still be at the bottom, just going to be bottom? That's the same thing.
Yeah, so it's just a question of where that bottom is, right? If they're actually learning it and passing the classes, that would be great. Mm-hmm.
It strikes me that there's to be a strong motivational component here where somebody knows the system, knows me really well, so I can either work on English or I can work on physics tonight, but I'm going to work on physics instead, so maybe I'll do better in physics. You have 168 hours in the week unless you're devoting more time,
That's right.
Your time. It'd be interesting to look at the other grades since that data is available.
That's a good question. So will the maybe enhanced effort that goes into physics hurt their other classes? It's certainly possible that would happen. And as a physics professor, I want about 120 of those 168 hours, and the rest of you will have to do it. No, I don't mean that seriously. But one of the things we're building into it is we want to know what other classes they're in. Because a very common problem for us is that they have organic chemistry tests the night before physics tests. If that's true for the student, we at least want to tell them a week in advance, remember that you have organic chemistry the night before physics, and do not wait until the day of the physics test to start studying. So that's not going to generate more hours for them, but it might help them use them a little better.
Right. Also, just the students can make excuses as well when the system is interacting with them so much. It just seems like it's going to be really hard if you're not doing well to have any justification by yourself. That would be a pretty strong motivator.
Right. Feedback on performance tends to help people. It's a good thing. It really does help them better assess where they really are, because people are not generally all that good at it. What we see, a very classic response is you don't understand how to do a problem. You ask somebody, they tell you how to do the problem, and you say, oh, I understand. Because you do, but that doesn't mean you can do the next problem. Right? So that's a crucial feedback loop in learning physics, is getting them to understand that understanding an explanation is not knowing the subject. Being able to do it is what we're asking you for. So.
Was there much work involved in getting MTS to accept the grades as the triggers for the very...
Right. No, it's completely generic. I mean, you define a data model for your project that includes whatever parameters you want, encoded in whatever way you want. So, if you think about the varied things people need to do around public health, they might care about where you live, or they might not. I mean, everything might matter. So, it's a fully flexible tool in that regard. You construct the data model.
This is probably further down the road. Have you thought about doing any follow-ups? Once they get out of the system where they have the nice tailoring and tells them make sure and study for your physics test because Orgo's coming up, the next semester, if they go on to another class, they don't have that. And I'm thinking
That's a good question,
of the research that's done on the electronic tether now, where the cell phones and mom is calling the kid the night before saying, remember you have to do this.
That's interesting. Yeah, no, that's interesting.
And what this then is going to train them to expect in terms of developing some of these skills, developing the motivation, and developing the self-discipline then to go out and do it themselves.
That's a good thing.
Successful farther on down the line.
Right, so this question is about whether we're going to coddle them too much and they'll actually not be able to do it without a system like this.
Coddle.
No, I'm sorry for putting that word in your mouth, but it's an interesting question that I hadn't thought about. And it's certainly something we should first try to think about how we exit them from it so that they get some message at the end that says, this isn't going to be here for you in your other classes. So we do get the chance to give them a summative kind of message that we hope will be saying, look, our first prediction for you was way lower than where you ended up. And you need to celebrate, right? I mean, I think that would be really nice to be able to do that for them.
But given the consistency of the performance data over time, they're not learning without the system either. So probably not too much harm.
That could be true. Yes?
Where is the front end going to reside, and how are you going to get students to look at it?
Okay, so it will be a web page that they see, right? And the way we will trigger them to know there's new information is they'll receive an individual email that says, there's new information on your eCoach site, and there'll be a link in it, right? We'll probably announce it sort of in class too, but an individual email will come with the link in it, so they won't have to remember and stuff like that. Anything else? Yes, Steve.
I'm curious about the predictive model in terms of the accuracy of the prediction in this model. How would you assess that?
Well, we just look at the dispersion around the prediction, right? And
to assess it on the sample on which it was initially estimated?
No. So you can make predictive models from the first half of the data and use them on the second and all that. It's a lot of data here.
Randomize.
So
you tested how to sample out a year, so that was from.
Yep. Yeah. So we looked at the term-by-term variation in this, and there is some. That term-by-term variation mostly comes from the fact that the grades actually move a little bit from term to term. So if you use the same predictive model across the whole thing, the grades are moving around by a few tenths of a grade, and the dispersion in the prediction is a half a letter grade. So it's there, but it's not a very major contributor.
But some of that's based on what was sampled, right? So that you're estimated on a certain sample, so that would be because you're sampling.
Absolutely right. So there's a bunch of sources of variation in that. You can look at it inside a class. I mean, they are 700 student classes, so questions you want to ask about that, you can split the data within the class and still have good samples and stuff. Okay, I think we probably should wrap up. Thank you all for coming. I hope you'll come to the other sessions that are later in the term.